Hi everyone, I'm Rachana Desai from the research team Altair RapidMiner. Thank you for listening in. Today I'm going to present a short demonstration scenario showcasing predictive model based interactive exploration for design time understanding of line of sight connectivity. This work mainly focuses on the analysis of the challenges and the opportunities for the machine learning in the channel modeling domain for both line of sight and non line of sight cases. And by applying the predictive explorations to the environmental and the wave level channel properties. The main objective here is to understand the feasibility of predicting the existence of line of sight and also analyzing the statistical relation between the attributes of the mobile channels and the geometrical link conditions in the dataset, which was supplied to us by our project partner Alto University. Now that we have a brief introduction, let me walk over the actual web application which was developed in the React in React programming language. So this is basically the user interface you are looking at. It has basically two tabs: homepage and the dashboard. So homepage basically describes the actual brief discussion about the actual problem definition and also the strategy that was used to solve this problem. Furthermore, we have three figures which basically gives the holistic view of the entire pipeline from data extraction to the prediction or the forecast made using machine learning. On the left hand side, figure one represents the blueprint for the outside side of the Helsinki Vantaa Airport Terminal 2, where the actual data and the readings were generated by our domain experts, Aalto University, using the ray tracing network tool. The environment contained two base stations at a very fixed location and 100 routes for each base station, where a mobile station was considered to be moving in each route, and each route has 150 data points. So for each route, a separate uniform distribution of a stationary pedestrian were also generated, some of which did interfere or obstruct the line of sight between base station and mobile station. On the right, you see the geometrical conditions, including the path law, delay spread, angle spread at both the base station and the mobile station. Also, the relative coordinates of mobile station, base station, and lastly, the likelihood of line of sight. And the bottom figure three basically shows the machine learning pipeline that was carried out in RapidMiner Studio. It basically shows how the condensed parameters obtained from the extensive channel sounding were constituted in a dataset, which was further used to train and test the machine learning models by using the RapidMiner ML pipeline. Now, this machine learning algorithms basically helps in extraction of important aspects of data for the potential forecast. Therefore, to strengthen the prediction capabilities of line of sight and non-line of sight identification without even knowing the specificity of the data, all tested machine learning systems were validated using the test dataset. And also, they were stored to further explore using our demonstration application, which I will show you in few minutes. But before that, I would like to mention that this use case scenario is a part of a very big major project, Ariadne, which stands for Artificial Intelligence Aided D-band Network for 5G Long-Term Evaluation. There are in total 12 partners whose logos you can see here, which collaboratively work for this project and for this particular use case. As I already mentioned earlier, the Aalto University was heavily as collaborative project partner for us. Now, walking over the actual dashboard application. This the main idea behind this dashboard application was to present a user interface and the associated features of the web based demonstrator application. So this was mainly developed as an interactive dashboard, and the main objective also was to assist the end users. It could be analyst or an engineer or a data scientist, so that they can understand the influence of various attribute values on the prediction that were made by the machine learning models. This demonstrator basically helps in explaining the predictions that were made by the machine learning model and the condensed parameters. And also this part of application basically focuses on various aspects, but I will walk over each one of them step by step. So as a first step was to import the data in the demonstrator, and this is performed by using import data, as you can see here. The only prerequisite condition for this import data is that the data set must contain the prediction and the label attributes for line of sight connectivity. Once you upload your data set, You can see the dataset in form of a tabular view along with all the attributes and the original label, LOS label, and the prediction label. Now, this problem was classified as a binomial classification under the supervised machine learning problem because of the two classes that we have, line of sight and non line of sight, which are represented as one and zeros respectively here in the table. Different machine learning models were trained to predict this prediction label, and the associated confidence score with each prediction, the confidence NLOS and confidence LOS, basically reflects the strength of this prediction that was made by the machine learning models. Additionally, the result of this uploaded data set can be seen here below in two panels. Now, on the left hand side, you can see the users can interact with various attributes in the data set, and can have a better understanding about how each attribute affects the forecast of the line of sight connectivity. So the user can adjust all the slider values according to their wish, and once the user moves them, they can see the impact of these values in form of bar chart, the pie chart, and the group bar chart. By manipulating the sliders, one can not only develop the intuition for the integrate models in form of this three charts, but can also select the data set by activating the show filter rows here. And by doing so, as you can see here, the data set is now narrowed to only two pages. And so this is the selected data set, which was selected based on the slider values the user selected here from the minimum and the maximum range of each of the attribute. Now, I will also try to showcase this by showing you a very short example how this interactivity works. So I will try to set the sliders. By setting the sliders to the different values, basically, you can see how the connectivity or the interactivity between the slider values are reflecting on the graphs that are on the right side and the bottom side. So with this current selection of changes in the path loss delay spread, azimuth spread for the base station, and elevation spread for the mobile station, I have changed the values a little bit. And as you can see here, that that with the current slider settings, the bar chart shows the most likely situation to be non-line of sight connectivity with 56.4%, and that of 43.6% for line of sight connectivity. The part, the pie chart, which is at the bottom, provides a clear comparison between the actual versus the predicted line of sight and non-line of sight cases. When we view together these two pie charts, it allows basically a visual interpretation of the confusion matrix. So when considering the current set of slider values that we have selected here, you can see that the predicted non-line of sight is a little bit less. That's around 7% less than the actual observed score for non-line of sight. And when it comes to the line of sight, you can see that the prediction score or the prediction value for the line of sight was little higher than maybe by 5 to 7% is little bit higher than the observed score of 37.5%. So you can clearly see the difference, and this basically helps for the to attest the good eye level of prediction accuracy. And on the third chart, that's the group bar chart, it confirms the differences between the line of sight and non-line of sight connection in terms of the actual versus predicted. And so here it further explains the model's prediction with the current set of values that have been selected for the sliders. So you can see here 56.4 and 62 is the prediction versus observed for the non-line of sight, and for the line of sight it's like 43 for the prediction, and 37 was the observed ones. So as we have seen how this slider value, the current set of values has been impacted on three charts, I would also like to make a point that for the analyst, it is also high interest to explore the most influential attributes for the subset of the data set that has been filtered out here. So for this particular data set that has been demonstrated in 2 pages and with the selected set of the values for the from the sliders, you can see there is one more chart, that's the correlation chart, which develops that interactivity by showing the positive and negative correlations of the attributes on the prediction. The chart shows the green and the red bars to the right and left respectively, where the green bar shows how certain the attributes, in this case, path loss, delay spread, and azimuth spread for both mobile station and base station, and are positively correlated, while the red bars that are elevation spread for base station and elevation spread for the mobile station are negatively correlated with the prediction. So we claim that all the charts here are interactive with respect to the slider criteria, and basically the prediction results depicted on in all the charts reflects the prediction distribution of line of sight versus non line of sight, and this basically satisfies the criteria that has been selected here for the slider values. So in this way, I would say that the complexity hidden in the model is better understood by the domain expert regarding the critical role different wave and channel properties play in the given environment. This understanding is very important for maintaining the reliable and continuous line of sight and non line of sight based connectivity. So, to summarize, I would say this kind of application showcased here would help the end users to quickly develop an intuition about the predictions that are made by the complex models. These insights may be very helpful when designing a network for coverage maximization of an indoor or probably an outdoor environment, or even deploying the machine learning models on the mobile station devices and making an autonomous decisions regarding the connectivity management. So, so yeah, that's it. Thank you so much for listening in.